Good morning. My name is Wei Hu. I'm from Nanjing University. It is my honor to present our recent work about open knowledge enrichment for long-tail entities. This is a joint work with my three students, Ermei Cao, Difeng Wang, and Jiacheng Huang. So, first, what is a knowledge base? A knowledge base is a semantically organized collection of entities, classes, and facts. A fact may describe the relation between two entities, or an attribute and value of an entity. What is the status of current knowledge bases? With the development of semantic web, linked data, and knowledge graphs, there are numerous knowledge bases on the current web. Some of them are very large, but they are widely acknowledged as incomplete. For example, let us see this figure. We analyzed the entity degree distribution of free base. We found that about 2 million entities in free base have less than 10 facts per entity, while there are 7,000 entities having more than 1,000 facts. So this figure shows that current knowledge base especially missing knowledge about long-tail entities. So our goal in this paper is to enrich long-tail entities with uncovered facts. We believe that this is very important for building a more complete knowledge base and benefit many AI applications. Based on an analysis, automation is inevitable. The cost of curating a fact manually is much more expensive than that of automatic creation, by a factor of 15 to 250. Existing automatic approaches address the knowledge enrichment problem from various angles, but they have two main limitations. First, they only tackle a part of the enrichment problem. For example, link prediction requires the head entity and the property are known in advance. Then it can predict the tail entity. Second, they lack specific considerations regarding non-tail entities. So in our work, we resolved two similar popular entities and widely available web data. Our idea is that to find out what a person lacks, see what other persons have. We argue that this may not be the best solution, but it's very intuitive and very efficient in practice. We also think that some non-tail entities just lack facts in KBs rather than in the real world. So we try to extract and infer true facts based on the various web sources. So let us see our approach in detail. We propose a full-fledged approach called OCLAY to enrich non-tail entities with uncovered facts from the open web, where prior knowledge from popular entities is leveraged to improve every enrichment step. Our approach consists of three main steps. First, property prediction. Second step is value extraction, and the third step is fact verification. In all these three steps, popular entities are leveraged. And we also want to address several challenges here. First, for non-tail entities, there can be a large number of candidate properties. Second, if we want to extract values, these values may be scattered over the web. Third, among the extracted facts, there are a lot of them may conflict with each other. So let us see the details. For the first step, for property prediction, we propose an attention-based graph neural network model. We first create an entity property graph. There are two types of nodes here, entity nodes and property nodes. And there are two types of edges, entity to property edges, which model the interaction between entity and property. And if an entity uses a property, we draw an edge. Second, entity to entity edges, which model the interaction between similar entities. Here, we employ three measures to find the top key similar entities based on type, property, and value similarity. These similarities are linearly combined together. For our graph neural network model, it consists of three modulars. First, entity modeling modular learns a corresponding latent vector representation for each entity. It aggregates three kinds of interactions: entity to property interaction, entity to entity interaction, and the embedding from itself. We use the attention mechanism to refine interaction coefficient, because we believe that some properties are more specific, and also some similar entities are more indicative. Similarly, property modeling modular learns a corresponding latent vector representation for each property. It aggregates two kinds of interactions: entity to property interaction and the embedding from itself. It also uses attention mechanism to refine the coefficient. Here, all the coefficients are normalized with the softmax function. Finally, the property prediction modular infers the probability that an entity has a property using a multi-layer perceptron with the sigmoid function. We use the binary cross-entropy as our loss function to train the model. After we predict properties, we want to extract values from the open web. To make use of the redundancy of web data and to ensure the coverage of the extraction, we consider three kinds of different web sources: semi-structured vertical website, unstructured plain text, and structured web tables and markup data. First, vertical websites contain high-quality knowledge for entities of specific type. For example, IMDb is about actors and movies. And for a vertical website, it usually contains a set of entity-detailed pages, which are generated from the same template or a set of similar templates. A detailed page can be regarded as a DOM tree, and a node in the DOM tree is reachable by an absolute XPath. The detailed pages using the same template share a common structure and placement of content. So here, our idea is to learn a set of X paths to property mappings based on popular entities, and use these mappings as template to extract values for long-tail entities. We also use CSS selectors to enhance the extraction. Second, plain texts are also very important. Here, we use the close information extraction technique with distant supervision. We leverage Stanford Co-NLP Toolkit with DBpedia Spotlight and N-gram index search for named entity recognition. We use the Wikipedia pages of popular entities as the annotated corpus for distant supervision. We implement the sentence-level attention over multiple instances with OpenNRE, which is a Python library for relation extraction. Third, to extract values from structured data, we conduct table search. We find related tables using the name and type of a target entity. Then we parse the found tables. We retrieve entity facts from tables. We distinguish vertical and horizontal tables here. A vertical table usually contains two columns. The first column is properties, and the second column is values. Differently, horizontal table contains several rows, and each row describes an entity. So we developed corresponding methods for them. Finally, we match table properties to the ones in the KB based on schema matching. In the third step, due to the nature of the web and the imperfection of the extraction method, conflicts often exist in the values connected from different sources. So, which values represent the truth? For example, given a long-tail entity Eureka and a predicted property nationality, we want to find out if USA or CA is the truth. Here, we propose a probabilistic graphic model to model the source reliability, fact truthfulness, and observations of facts from sources. For each fact f, we model its probability of being true as a latent random variable zf, and generate zf from a beta distribution. Here, we use beta distribution because it is often used to describe the distribution of a probabilistic value. For each source S, we model its variance omega s by the scaled inverse chi-squared distribution. We use this distribution for two main reasons. First, it is a conjugate prior for the variance parameter of normal distribution, which keeps the scalability of model inference. Second, it can conveniently handle the effect of sample size to tackle the problem of long-tail. For each observation OFS of fact F from source S, we assume it is drawn from a normal distribution with mean ZF and variance omega s. We believe that the observation of facts from sources are likely to be centered around latent truth and influenced by source quality. So overall, the likelihood of all observations and latent variables is like this. To infer truth, we need to find the maximum posterior estimate for z. Based on the conjugacy of exponential families, we can directly integrate out w, then apply a gradient descent method to optimize the likelihood and infer the unknown truth. After we obtain the inferred truth, the posterior source reliability can also be calculated, which has a closed form solution. Please find more details in our paper. We conduct both synthetic and real-world experiments here. Our goal in the synthetic experiment is twofold. First, we want to conduct modular-based evaluation of our approach and compare it with related models. Second, we want to test various hyperparameters and use the best ones in the real-world experiment. So, in the synthetic experiment, we prepare our dataset based on freebase. We selected 10 freebase classes, which are popular and familiar with people. For each class, we sample 1,000 entities for training, 100 for validation, and 100 for testing. All these entities come from top 20% of entities by property numbers. So in this synthetic experiment, we simulate non-tail entities based on popular entities. We randomly keep 5 properties and related facts, remove the others as ground truths. First, let us see the result of property prediction. Here, we consider 3 categories of comparative models. First, the first category is the approach to mine properties in knowledge bases. The second category is the models widely used in recommender systems. And the third category is based on deep neural networks. We can see that the second category generally performs better than the first category, which demonstrates the necessity of modeling customized properties for entities, rather than just mine properties for classes. If we compare the third category and the second category, the neural network-based models show their power in recommendation. And finally, if we compare Oakley with the deep neural network-based models, Oakley shows the superiority in modeling different strands of complex interaction, and it achieves the best results in all metrics. Second, let us see the result of value extraction and fact verification. First, Oakley value extraction gains the lowest precision but the highest recall, as it collects all values from the web, and all these values are used by the other approaches. Here we also consider 3 categories here, namely iterative models, optimization models, and probabilistic graphic models. By comparison, we find that Oakley obtains the best precision and the F1 score. So in the real-world experiment, we use the following setting. We use the same 10 classes as before, but for each class, we sample 50 real long-tail entities. We predict 10 properties for each non-tail entity. Each fact is judged by 3 students, and we measure the level of agreement between them, and the result is pretty good. Because the complete set of facts is unknown, in the real-world experiment, we can only measure precision. So let us see the result. As far as we know, there is no holistic method that can enrich non-tail entities from the web. So we decide to combine the 2 second-best models together as a competitor. Based on our result, we found that Oakley is generally good and significantly better than GMF plus CATD. Second, the number of verified facts in class film is significantly more, and it also holds the highest precision. We found that this is because there are a lot of high-quality web portals for films. However, in contrast, Oakley obtained the lowest precision in class album. We look at the results and find that for popular albums, they usually contain a property about a word. But for non-tail albums, they don't receive any award yet. But if we use a word and try to find the corresponding values, we may get the wrong result. Also, the albums often have very similar names, which cause the disambiguation problem. We also analyze the proportion and decision of facts from different kinds of sources. We gain several observations. First, vertical websites account for the largest proportion and structured data for the least, because most facts obtained in structured data are also found in other sources. Second, overlap holds the highest precision. Here, overlap means that the facts are from at least 2 different kinds of sources. For example, vertical websites and plain text. Third, in the real-world experiment, the proportion of vertical websites declines, while the proportion of plain text increases. We owe it to the fact that few people would like to organize the information for non-tail entities in structured or semi-structured form. So in conclusion, in this work, we proposed Oakley, a full-fledged approach for open knowledge enrichment on non-tail entities. It contains a novel property prediction model based on graph neural network and attention mechanism. It also contains a factor verification model based on probabilistic graphic model with conjugate priors. Our experiment shows its feasibility and superiority against the various competitors. For future work, we plan to optimize key modulus to accelerate the enrichment of speed. We also want to study full neural network-based architectures. That's all. Thank you for your time. If you are interested in our work, please find our dataset and source code on GitHub. And I'm ready to answer any questions.